Hi everyone. So welcome to this video. In this video, we'll be doing an example problem, problem 9.8 in the Dean textbook. And the idea behind this problem is to give you some more practice of order of magnitude analysis for the case of boundary layers. So you can recall that we discussed this in class in the last week that uh, basically boundary layers are important to calculate the viscous effects near the surfaces of walls, right? And then in this week we also did a problem for during the recitations where we did scaling analysis for power law fluids, right? So what we want to do in this particular video is that we want to go ahead and start looking into different applications of boundary layer analysis. So this is problem 9.8 and I encourage you to go ahead and read the problem in the book. So the problem deals with a circular pipe, and the problem talks about this assumption that we were saying till now of fully developed flow, right? So whenever you would see problems in unidirectional flow, for pipe flow, for flow Pocell flow between two plates, and similar things, we always talked about this assumption of fully developed flow. And if you recall, what we generally used to say is that in fully developed flow, del V x by del x was equal to 0. That the velocity was no longer changing in, if the velocity was in x direction, it was no longer changing in the same direction, right? So what we want to do in this problem is to really understand when can we actually make this assumption of fully developed flow. So till now we were always given this, but now we'll actually see how we can do this. So I've taken this image from the book, and let me write this as z is equal to 0 here. This is z between LE and less than 0, and this is z is equal to LE. So please go ahead and read the problem. So the what the problem is trying to ask us is wants us to estimate LE. And what is LE? So let us say we have a pipe which with some length going, and then the radius, the diameter is d. So when you input some fluid inside this, initially the fluid will have uniform velocity at the entrance, right? So so whenever we had a pipe, you can recall that when we call this as z and this is r, when we calculate velocity profiles in problem, we always had velocity profile as a parabolic velocity profile. And however, so that meant that the velocity is different at different r. For a particular z, the velocity is different at different r, and the velocity is no longer changing in z, because we could assume that del b z by del z is equal to 0, or that was the fully developed flow. But what we are saying is initially at initially means at z is equal to 0, at z is equal to 0, when we will enter something, we'll enter something with a uniform velocity, right? And when it enters, because of no slip condition here, some fluid will have a less velocity, and then velocity will become like this, where in middle you will have uniform velocity, at the end towards you will have no slip condition, basically bringing in effects at different r, and at the end you will basically, after some point, you will have where you will get perfectly parabolic velocity, and then it no longer changes. So what is this entrance length till which the velocity profile is developing, right? So that was the meant of developed flow, that velocity profile is actually developing until after that it no longer changes with x. Okay, so we have to estimate this LE, or the entrance length. And you can imagine that basically this is like saying that you have flat plates which have boundary layers like this from one side, and and you have another side here, and basically the boundary layers come and meet. So when the boundary layers will meet, at that after that point, basically the entire region is now governed by is dominated by viscosity, right? So boundary layer is a region where viscosity dominated by both viscosity and inertia, right? So boundary layer is the region where viscous forces matter, and the region outside boundary layer is the region where viscosity does not matter, right? So now we are saying is that uh, when the two boundary layers will meet from both the sides, if you have two plates, two parallel plates, then this region where the two boundary layers meet, now the entire region will have the effect of both viscosity and inertia. So that's the kind of conceptually what do we mean by fully developing. So in this region, velocity is changing as a function of x, and you can imagine it is changing as a function of x because here initially all elements at the same velocity initially, and but when you go here, velocity is changing. Basically, there is no, at a different r you have different velocities. So for instance, velocity is maximum in the center and zero at the end. So that's why you want to make sure that velocity has to vary on x, because if it is constant initially here, then it is becoming a parabolic profile at as you're going along z. So it is actually developing over the z direction. So now let us think about how we will solve this problem. So if we have to estimate this length, how will we estimate this length? So let's first start with our order of magnitude analysis, which is what the problem also suggests us to do. And for order of magnitude analysis, we will go back and pick up the equations that we have been doing till now, which is basically we'll first do the equation of continuity, and then we'll do equation of uh, Navier-Stokes equation. So for equation of continuity and Navier-Stokes equation, we can also make some assumptions. So let's also write our assumptions. So we can assume the flow to be steady, right? So that's a reasonable assumption to do, that the flow will be steady. So we can drop off the time term, and we can make rho and mu or constant. And because it's a pipe, we can also assume the del by del theta is 0, or it is axis symmetric. Okay. So now let us discuss the equation of continuity in the cylindrical coordinates, and within the cylindrical coordinates we will assume that the del by del theta terms and v theta is equal to 0. Okay. So let's look at the continuity equation. The continuity equation is 1 by r del by del r of r vr plus del by del z of vz is equal to 0. Okay. So this is the continuity equation. And if you want to scale, do order of magnitude analysis, we will be basically have to predict the scaling values of each term. So let us scale VR as UR, and VZ can be scaled by average velocity U average, right? Because let us call this velocity here that we are inputting as U average. Okay. And delta R is basically radius, and delta Z is basically length. So why am I doing delta R as radius is because what we want to basically find is when the boundary layer is developing, at which point the boundary layer thickness actually becomes equal to the radius, right? Whenever the boundary layer thickness will become equal to the radius, we can say that from both the sides the boundary layer has come, basically boundary layer is developed and met, and then from there on you will have fully developed flow. So you can assume delta R to be R, delta Z to be LE. Alright, so we have this, and now let us do the order of magnitude analysis on equation of continuity. So if we do that, we actually get that UR, so you can easily see that you will get UR by R is similar to UZ by LE. Okay, so this is one equation. Then second we will go, and what we will do is we will look at the Navier-Stokes equation. So this was the equation of continuity. Now we'll have to go to Navier-Stokes equation in z direction. I am taking z direction, as you can recall in the class when we did the Navier-Stokes equation in x direction, which gives us a useful information about the scale of boundary layer, right? So we'll go and do the take the Navier-Stokes equation in z direction. So let me pull out the equation for Navier-Stokes equation. So this is in table 6.9 in the book. So here is the equation, and I'm assuming steady flow, so I do not have any time term here. And again, I'm using axisymmetric flow, so I'll not be writing those equations, those terms basically. I'll be just directly writing the relevant terms. Okay. So this is rho Vr del Vz by del R plus Vz del Vz by del Z. This is the left hand side is equal to minus del P by del Z plus mu 1 by R del by del R of R del Vz by del R plus the last term will be del square Vz del Z square. Okay. So let us call this term A, this as B, this as C, and this as D. Okay. So we can scale each term now. So the first term would be rho UR U average or UZ. Sorry, let me just correct this as call this as U average to be consistent. I forgot to. So this will be U average here by R. This is term A by R. Then the second term is rho U average. So this is this term. So in the first term was UR into U average by R, right? UR into U average by R. Now the second term will be U average into U average by LE. U average into U average by LE. So if you use equation of continuity, this both of them equations become same. Rho U average square by LE. Okay. So basically the left hand side scales by rho U square by LE only. So both of them term are scaling equally. So both of them have equal importance. So rho U square by LE. Now the term C, which is the viscosity term. So now let's scale this one. So this is mu and 1 by R, and this will get cancelled, and you will have UZ by R square, and UZ is U average. This is mu U average by R square, and D you will have mu U average by LE square. Okay. So let me now write the full equation with the terms. So last term was mu U average by LE square. Okay. So now let me have all the terms here. So A plus B can be simply, and the equation is A plus B is equal to C plus D, right? So A plus B here is actually similar to U average square by L, and then C is mu into U average by R square plus mu U average by LE square, right? Now in a normal balance, when we did not have this thing of a pipe flow, rather than R, we actually had delta there, right? And LE was actually just length. Now because the flow is bounded here, our boundary layer cannot grow after one point. Our boundary layer is sort of has to grow only till the center, or till the point it reaches the radius of the pipe. And because of that, actually, as you will see that there are some differences between the other analysis. So in the other analysis, in the one we did in class and in recitation, this was mu u average by delta square and this was mu u average by L square, and we said that delta is much less than L, so we actually ignored this LE term and just had mu u average by delta square, and we could then calculate the relationship between delta and sorry, this is LE here, yeah, and delta and LE. But here we cannot do that, and the reason is because depending on Reynolds number, we'll have different sort of flow pattern. So let us divide the whole equation. So we want to create basically we want to create Reynolds number. So let's just divide everything by mu u by r. So basically what I'm trying to say is we have u average square here, right? And if I divide mu u rho u square by le, and then I divide here mu u average by r, and sorry, by r square, then this will become 1 plus r square by le square. So what I'm saying is divide everything, divide by mu u average by r square. Alright, and why am I doing this? Because this will become rho average r by mu into r by le, and scale says r square by le square. Okay, uh, and what this is telling me is that, and this is actually not exactly Reynolds number, but this is half of Reynolds number, but we can call it similarly to Reynolds number. So this is Reynolds number into r by le is 1 by r square by le square. Okay, so now uh, we have few cases possible here. So we have two cases possible, is that r is greater than 1 and r is much less than 1, and the book talks about both of these cases. So again, the difference between the initial problem that we did in class and in this problem is that you cannot just ignore the terms here, because they may be comparable to each other depending on the case, and because of that you may have to uh, you may get different solutions. So the problem talks about these two cases, and Reynolds number greater than 1 and Reynolds number less than 1. So if Reynolds number is greater than 1, the logical thing to do would be to take this and divide everything by Reynolds number, right? And that means that Reynolds number is greater than 1, then we can actually approximate r by le as 1 by re, and basically ignore this term. And why am I ignoring this term? Because if r by l is 1 by re, then r square by le square will be 1 by re square. So this will become 1 by re cube. This term will become 1 by re cube, which is much smaller than 1 by re if re is greater than 1. So basically we are saying is that uh, le by r will be proportional to Reynolds number for Reynolds number greater than 1. Okay, so I hope this made sense. So basically we could ignore this term, this part, for Reynolds number much greater than 1, and just basically use this term as the part of the viscous contribution. Then if other extreme of re less than 1, other extreme of re less than 1, in that case what we can do is you can just ignore this term. You can imagine that we can ignore this term because this is a very small coefficient with r by le, and that will say that 1 plus r square by le square is equal to 0. And because order of magnitude analysis, magnitudes don't matter, basically we are saying that r by le is of the order of 1, or the signs don't matter in order of magnitude analysis, or le by r is actually equal to 1. Sorry for the bad writing. Uh, this is le by r is of the order of 1. Okay, for re less than. So when you have low Reynolds number, basically your entrance length is of the magnitude of Reynolds number. But if you have high, my mistake, your entrance length is of the order of radius. But if you have high Reynolds number, your entrance length is Reynolds number times r, which means that basically at high Reynolds number you will take longer distance to get to the fully developed flow, and which makes sense because for a flow to fully develop, if you have a high Reynolds number, as you have read in the class, that the thickness is thinner, so it takes longer to reach the center of the tube. But if you have low Reynolds number, it reaches almost on the order of magnitude of the radius. So if you look in the problem, the book also suggests you to look in the exact solution of this problem. And if you so there is an exact solution of this entrance length, and that has been given in equation 12.2. So that's chapter 12, not something we have not covered. But the exact solution is Le by R is 0.49 plus 0.11 Re, and we get the same trends, right? That for Re less than 1, you ignore this term and you will get Le by R is constant, and for Re greater than 1, for this one you will get Le by R is proportional to Reynolds number, and you will ignore this term. Okay, so hopefully this made sense of what we were trying to do. So it was something a little bit new, that we did not ignore both one of the two terms from the viscous scalings, and that was because the problem in itself asked us, and also we couldn't ignore because we did not really know that whether delta, which in case of this was R, and that delta by L is much less than 1. We did not know that. In this problem, we were actually trying to find Le. In generally other problems, we were trying to find delta, right? So that is also one of the different, you can think about it. Then in the problems that we were doing in class, we were actually finding the boundary layer thickness. Here we knew the boundary layer thickness would be radius, and we were trying to find the length. So we did not know this, and that's why we did not ignore the two cases and just used the two different cases of Reynolds number to find the solutions. So let me recap the problem, what we did in this problem. So we were given the problem that we had to calculate when can we assume the fully developed flow, and then we discussed that because when the flow comes initially, it is completely uniform, and the velocity evolves as it is going in within the pipe, and after some distance the parabolic profile becomes completely parabolic. And to explain this using boundary layers, we said that when the boundary layer grows from both the sides and meets in the center, in case of parallel plate or similar to like a pipe flow, it will happen that when the boundary layer becomes the half of the distance between the two plates, or it becomes equal to the radius in case of pipe flow, basically the velocity will no longer change with distance, and that is the condition we want to sort of find when basically both sides meet and the whole region basically becomes fully developed. And we made some assumptions, and then we had continuity equation and used scaling analysis, and then we have Navier-Stokes equation in z direction, and we used scaling analysis. And the new part here was that we scaled delta by r and length by the entrance length, and then we could not ignore we just couldn't ignore one of the terms without knowing the Reynolds number we are in. So when we wrote this equation, then we did two cases of Reynolds number much greater than 1 and much less than 1, and then finally we got the limiting case that Reynolds number length will be proportional to Reynolds number for higher Reynolds number, which made sense that it will take longer if you have higher velocity, because the boundary layer grows, the growth of boundary layer is very slow, so it takes longer to reach the center for boundary layer, and when you have low Reynolds number, it is basically similar to the radius. And then this was this variation matched well with the exact solution. So I hope with this problem, with the one we did in class for viscoelastic, for non-Newtonian fluids, and the one discussed in class for regular boundary layer approximation, you can appreciate the importance of order of magnitude analysis, and that it gives you a good flavor of practice. So feel free to give us any feedback, and see you in the next video.